Okay, guys, so that heading of the top of that page there says tangent to circle given. So guys, this is basically just a summary of things that we can do if we have a tangent. Alright, we have been using it before. We know tangent perpendicular radius, right? We've used that a bunch of times. We know that a radius is always perpendicular to tangent. So if you have that, you can use that, obviously. So I'm just going to highlight that reason, because that is the reason that we would have to write down. No tangent for a common point, right? You have to write tangent for our tangent. That theorem says that if you have tangents coming from the same point outside the circle, those tangents are equal, right? So guys, remember, it's not the whole tangent, because this tangent can be drawn forever and ever, right? It's just the section from that point to where it touches the circle. Okay, so it's just those two parts that are equal. And then we looked at that and we say that that actually forms an isosceles triangle there, which means that those two angles will also be right. So that's usually how we use it. But guys, it also came up quite often in exercises where they give you two radii and then it's a height. Right? We've used that once or twice before. Okay, so sometimes you need to use the lengths, often you have to use those angles. Then, let's just highlight that reason. Then at the bottom there we have two different pictures just of the same thing, right? Tan-chord theorem. We use that a lot as well. The tan-chord theorem, remember the angle between a tangent and a chord, so x is equal to the angle subtended by the same chord. So guys, is this the only case of tan-chord theorem in this picture that we could have used? I'm going to take a red one. I could have used this angle here, right? That is a good angle between the tangent and this chord. So that will be equal to the angle subtended by this chord, which is that angle over there. Okay, so just add that in on your picture. Those two angles will also be. Then the other picture is the same thing, it's just drawn differently so that you can see that it works with obtuse angles as well, angles that are bigger than 90. I think this did come up in one question, right? Where it was a big angle. I remember it was still two or three angles together that was equal to the one there. So again, here, this is the angle between the tangent and this chord. So it must be equal to the angle subtended by that chord, is the thing. Guys, again, we could have worked with this angle on this side as well, right? That one there. It's also an angle between the tangent and this chord. So it will be equal to the angle subtended by this chord, which is up there. Right? That will also be the angle there. Now guys, just like what we just did with cyclic quads, right? Where sometimes they give you a quad that's not drawn in a circle, but you can prove that it could be drawn in a circle, right? In the same way, sometimes they can give you a line that doesn't look like a tangent, that doesn't touch a circle, but you can actually draw a circle in so that it is a tangent. So that is now the next section, the second part of this page. How to prove that a line is a tangent. Okay, even if the circle is not drawn, guys, it can be a picture without a circle at all, and they can ask you, prove that AC would be a tangent to a circle at point B. Right, that could be the wording. So I'll just add that at the top maybe so that you can like identify the question. So they will say for the first one, let me just say, for example, prove that AC is a tangent to a circle at point B. So guys, then we're going to do what we know about tangents, and we'll see if we can prove it. Right? So just imagine that the circle wasn't actually there, but then we know that this is a 90-degree angle here. Right? So guys, we know that a tangent always has to be perpendicular to a radius, right? At the point of contact, at that point B that they're talking about here. So if you have a line that's perpendicular to another one, right? Then it could be that the one line is a radius and the other one is a tangent. Now, if I can find an example, it actually isn't an example in this book, but I have seen some examples of what. And then we can also do like a important reason, converse tan perpendicular radius. That converse reason always comes in there. So that whenever you're proving that it's a cyclic quad, when you're proving that it's a tangent, you're proving that it's a diameter, you have to use the word converse. The other one is we need to show that tan chord theorem works. Right? Because guys, the only reason or the only way, for tan chord theorem to work is if it is a tangent and it is a chord to a circle. Okay? So here I wrote that DCE, this line, is a tangent if C1 is equal to A. So if we somehow can prove that these two angles are equal, right, and that circle is not drawn, okay, that's the important thing that you must realize here. The circle is drawn in a picture, yes, but in a question it won't be drawn. Okay, so it will just like be this triangle shape and this line. And they can say, prove that DE is a tangent to the circle at C. Right? And then the circle might not even be. So if you can prove that C1 is equal to A, then it is a tangent. What else? If I can prove that this angle, ACD, is equal to B, then it also is a tangent. Again, reason will be converse tangent here. Okay. Once I have already decided what I'm going to do, guys. Got it. 5, 6, yes. Okay, I want you guys just to practice some more of the kind of more difficult questions. So where they ask you to prove things. I'm going to check now, guys, if I can find one where you just prove that it's a tangent. I just didn't have time to think for us. So it's exercise 6. I'll put the question on the board now. On page 207, number 5. Guys, tomorrow